Year 13, Chapter 5, Differentiation, Lesson 5, the Quotient Rule. So let's use an example to introduce why we might need another rule for differentiation. I want you to look at the function y equals x plus 5 over 2x minus 1. Now, this is not a composite function, and it's expressed in a form that doesn't naturally suggest it is a product. So there is then an opportunity for us to look at using a third rule of differentiation, a rule which is set up if your function y is of the form u over v, i.e. a quotient, where u and v would be functions of x. Now, as we've done previously, we're going to introduce what the rule is, and we'll then look at using it. So if y equals u over v, where u and v are functions of x, then the quotient rule tells us that dy by dx, the derivative of y with respect to x, is equal to v multiplied by du by dx, take away u multiplied by dv by dx, all divided by v squared. Now let's take a look at the example that we introduced a moment ago. Y equals x plus 5 over 2x minus 1. Now, we could, in theory, differentiate this using the product rule. And that's exactly what we're going to do in a minute. Have a think about how we could rewrite this so it's in the format of a product rather than a quotient. We can leave x plus 5 as it is, but this part, 2x minus 1, we can rewrite as 2x minus 1 to the power of negative 1, so it joins the x plus 5 in the numerator rather than existing as the denominator. And we now have a clear product. Look at the two constituent parts of it. So u would be x plus 5, and I can differentiate that to give me 1, differentiating with respect to x, and v would equal 2x minus 1 to the power of negative 1. Now that's a composite, so when I differentiate it, I'm making use of the chain rule, and hopefully you see by now why we have to use the chain rule so quickly and efficiently. So multiply by the power of negative 1, reduce the power by 1, so it's negative 2, and then multiply by the derivative of the inner function here, which of course is 2. So this then gives me negative 2 bracket 2x minus 1 to the negative 2. Let's remind ourselves of the product rule that dy by dx is equal to u multiplied by dv by dx. So this pair here multiplied together, plus v multiplied by du by dx. So this pair here multiplied together. So let's put these components together. So u multiplied by dv by dx first of all. So that's x plus 5 multiplied by negative 2 to x minus 1 to the negative 2. And then add v multiplied by du by dx, but du by dx is just 1, so this then gives me 2x minus 1 to the negative 1. Now, as we've done previously, we're now going to factorize this. We've actually done the differentiation, but let's factorize. Now, do we have any common factors? Well, look here, we've got 2x minus 1 to the negative 2, and 2x minus 1 to the negative 1, and remember we always take out the lower of the two powers, which of course is a power of negative 2. So 2x minus 1 to the negative 2 comes out. We'll use the large square brackets for clarity, and what do we have inside our brackets? Well, we have a negative 2 and x plus 5 here, and then for this part here we need to make sure that whatever we have here multiplies by 2x minus 1 to the negative 2 to give us 2x minus 1 to the negative 1. So of course it's got to be 2x minus 1 to the power of 1, because then the powers will add together, negative 2 plus 1 will add together to give us the negative 1 power overall. Now simplifying this a little bit further then gives me 2x minus 1 to the negative 2 outside, and then the part in the large square brackets actually simplifies to give me negative 11. So I can write the final answer as negative 11 over 2x minus 1 all squared. So even if a function is expressed as a quotient, we could actually use the product rule to differentiate it. But it is by far simpler in a lot of these cases to make use of the quotient rule. So let's have a go at doing this, and we will do a compare and contrast here. So remember, our function y has got to be expressed as u over v, so it's got to be expressed as a quotient. Now, what are the two constituent parts? Well, u would be equal to x plus 5, and v would then be 2x minus 1. It is not 2x minus 1 to the power of negative 1, because if you look at the comparison here, v is just the denominator function, which is just 2x minus 1. Now, let's differentiate these parts here. So du by dx is equal to 1, and then dv by dx is equal to 2. So the differentiation is even simpler because we're only differentiating v as 2x minus 1. So it's a much, much simpler piece of differentiation. Now, the quotient rule then tells us that dy by dx is equal to v multiplied by du by dx, subtract u multiplied by dv by dx, and then the whole thing is divided by v squared. So let's fill in the different components of this. So we need v times du by dx first of all, which is just 2x minus 1. And we're subtracting from that u multiplied by dv by dx, which gives us 2 bracket x plus 5, and then the whole thing is divided by v squared, which of course is 2x minus 1 all squared. Now simplify the numerator and you'll find very quickly you get negative 11, and then we have negative 11 over 2x minus 1 all squared, which is the same answer that we got here using the product rule, but with far fewer steps of working. So it's a much more efficient way of differentiating a function that is expressed as a quotient. So have a look at this example. You're going to try this yourselves. Feel free to pause the video, try it yourself, and then check the answer. Or if you feel like you need a little bit more support with this, work through the video as we differentiate this function. So we need to identify that this is u over v, and we then need to look at the constituent parts in a little bit more detail. So we have u equal to x cubed, so du by dx is equal to 3x squared. We then know that v is equal to 2x minus 1, not 2x minus 1 all to the negative 1, it's just the denominator function, and dv by dx is equal to 2. Now, the quotient rule tells us that dy by dx is equal to v multiplied by du by dx, subtract u multiplied by dv by dx, and it's all divided by v squared. So we just need to substitute in the component parts. So v multiplied by du by dx first of all. So 2x minus 1 multiplied by 3x squared. And we want to subtract from that u multiplied by dv by dx, so x cubed multiplied by 2, and then the whole thing needs to be divided by v squared, which we'll of course express as 2x minus 1 all squared. Now simplify the numerator carefully, so we have 6x cubed minus 3x squared minus 2x cubed all over 2x minus 1 squared. So this then simplifies to give us 4x cubed minus 3x squared all over a denominator of 2x minus 1 all squared. And we could, if we wished, factorize the numerator as well. So let's have a look at another example together. You can see the function expressed as a quotient here. Now, the denominator is not really expressed in the easiest format, so we'll leave the numerator as it is, but the denominator part, we'll express it as x subtract 2 to the power of a half. And then we need to make sure we can see the u and the v distinctly, numerator and denominator. So u is equal to x plus 5 squared. V is equal to x minus 2 to the power of a half. So this time we have two composite functions, and we're going to have to make use of the chain rule to differentiate these. So du by dx, that's a simple one, multiply by the power of 2, reduce the power by 1, so it becomes 1, and then multiply by the derivative of the inner function. Well, the derivative of x plus 5 is just 1, so that's done. A bit more complex for v, dv by dx, multiply by the power of a half, reduce the power by 1, so it becomes negative a half, but again, the derivative of x minus 2 is 1, so multiplying by 1 doesn't alter what we have already. So now, let's write out the quotient rule. So we have this ready for use. dy by dx is equal to v multiplied by du by dx, subtract u multiplied by dv by dx, and then the whole thing divided by v squared. So all we now need to do is substitute into the component parts of this. So v multiplied by du by dx here gives me 2x plus 5 and x minus 2 to the power of a half. Subtract, and then these multiplied together, a half x minus 2 to the negative a half, x plus 5 all squared, and then the whole thing divided by v squared. Now, v is equal to this. So if you square that, we'll just get x minus 2. So we're done. Now, let's have a look at how we can then simplify this, because there are a number of different ways in which we might like to simplify this, and let's take a look at these. We've done the differentiation, but now how do we simplify and factorize the result? Now, the first thing I'm going to do is, because both parts here contain x minus 2, although raised to different powers, and then there's an x minus 2 in the denominator, I'm going to simplify and divide both parts of the numerator by x minus 2. So I have 2 bracket x plus 5, and then here I've got x minus 2 to the power of a half being divided by x minus 2, which is raised to the power of 1, effectively. So subtract the powers because it's a division, and I will get x minus 2 to the power of negative a half. Subtract, and then again I'm going to just write in this part here, x plus 5 all squared, and then I have to look at the fact that I've got x minus 2 to the negative a half being divided by x minus 2 to the 1. Again, subtract the powers here, and I will have x minus 2 to the power of negative 3 over 2, or negative 1.5. And I mustn't forget that there is a factor of a half here as well. I'm now going to look for common factors. Now we can see very clearly that there's a common factor of x plus 5 that could be factorised, and hopefully we can also see very clearly x minus 2, some power of this can be factorised as well. So the first thing I'm going to do is look at the numerical values, and this is something that often confuses people. We've got a factor of 2 here, and we've got a factor of a half. So what can we take outside the bracket? Well, we're going to have to take out a half, and you'll see how this works in a second. Then let's take out x plus 5, and then let's take out x minus 2 to the power of negative 3 over 2. Again, we have to go with the lower of the two possible powers. Now, I then want large square brackets for clarity. Now, when we multiply back, the first term needs to end up with a factor of 2. So what multiplies by a half to make 2? Well, it's 4. 4 times a half is 2, and that will give me this 2 here. I don't need to do anything with the x plus 5, but I do need to have something here so that when these two terms are multiplied, the overall power will end up being negative a half. So this has to have a power of 1, because 1 add negative 3 over 2 gives me negative a half. I then want a subtraction, and I don't need anything numerical there because I already have the half outside, but I do need an x plus 5, so I'll get x plus 5 all squared, and then I don't need anything else because I've already got my x minus 2 to the negative 3 over 2. Then just simplify everything carefully, so we end up with a half, x plus 5, x minus 2 to the negative 3 over 2, and then the part in brackets simplifies to give me 3x minus 13. Now, sometimes we then like to write this in a fractional format. So the numerator would contain the x plus 5 and the 3x minus 13. And the denominator would contain the 2 and x minus 2 to the power of 3 over 2. Now, we're going to have a look at how we derive the quotient rule, so where does it actually come from? So let's start with y equals u over v, where u is some function of x and v is some function of x, which means that u and v can both be differentiated with respect to x, which means that du by dx and dv by dx can be found. Now, I'm going to rewrite this as u v to the negative 1, and we're then going to apply the product rule. So let's explore the two parts of the product. One part of the product is u, and if I differentiate that with respect to x, I simply get du by dx, so that's easy. The other part of the product is v to the power of negative 1. Now, to differentiate this, I'm going to need to use the chain rule because it's something being raised to the power of negative 1, but we don't know what v is. It could be 2x plus 4, it could be 7x minus 8, etc. So to differentiate it, apply the chain rule. So multiply by the power, negative 1. We then reduce the power down to negative 2, but we have to multiply by the derivative of what's inside. So we need to multiply by dv by dx, and that is what we get when we differentiate v to the power of negative 1, because remember, we are differentiating with respect to x. Now, this little process that I've used here is something we call implicit differentiation, because we are differentiating v with respect to x, even though we don't know what v is specifically in terms of x. And you'll learn about that in the next chapter of differentiation. Now, the next thing I need to do is apply the product rule to this. So remember, the product rule works in pairs. We need u multiplied by this, and then the other way around, we need this multiplied by this, and we then add these parts together. And it doesn't matter what order we do it in, because as we know with the product rule, you're adding, so you can do it in either order. So the product rule tells me that dy by dx would be equal to v to the negative 1 multiplied by du by dx, and then add u multiplied by negative v to the negative 2 multiplied by this dv by dx. Now this really needs some tidying up. So we've got 1 over v du by dx minus u over v squared dv by dx. Now I'm going to take the term on the left here and I'm going to rewrite this as v over v squared, which is of course an equivalent fraction. This will make it easier for me to factorize out 1 over v squared. Be careful, that's a v there. And I'm left then with v multiplied by du by dx minus u multiplied by dv by dx. And this should be very familiar to everybody as the quotient rule. V multiplied by du by dx minus u multiplied by dv by dx all over v squared. And this is dy by dx. So the quotient rule can be derived using the product rule.